Yeah. Okay, thank you. Alright, so good afternoon everyone. Okay, so quick recap of what we have done so far. We have sort of characterized what mutual dependence looks like in a matching code graph. Right? This result basically tells you that two edges are mutually dependent, E and F. If and only if you consider G minus F, then there is a barrier B that contains both ends of E, well, which is why E is no longer matchable, right? But now we can go further. Because of mutual dependence, we can actually conclude that there are no other edges that have both ends in the barrier, right? So this is the point where we actually use mutual dependence, and we can also conclude that actually all of these components are just odd components. There are no even components, and further that for every component of G minus F minus B, the cut corresponding to that component is a tight cut. Right? So all of these things are things we concluded last time. Good. And this is going to be very useful towards our main result of this chapter, which says that if you have a minimal class of cardinality 3 or more, then that set of edges contains a pair of two edges that comprise an even two cut of the graph. Right? If I give you a minimal class, let's say it has 10 edges, well, its cardinality is more than 3 or at least 3, then in that set of 10 edges there will be two edges that comprise an even two cut of the graph. In particular, when you delete Q, the graph will disconnect. Therefore, such a minimal class cannot be a removable class. The conclusion of this is that a removable class in any matching code graph has cardinality 1 or 2. Yeah, let's look at one example. So this is an example you may have seen before, especially if you were in ISI for any of my talks, or maybe in the math department also I gave this same talk. So here's a nice matching code graph. It is also cubic, and observe that these edges, not only do they comprise a perfect matching, they all actually depend on each other. If you pick any of these yellow edges, then you are forced to pick all of the other yellow edges in a perfect matching. So this is an equivalence class, and it also follows that no other edge can depend on this. Right? If any other edge depended on this class, then you would have a perfect matching containing the yellow edges and one more edge. Right? So these all edges depend on each other and nobody else depends on them. Therefore, this is a minimal class. This is an equivalence class and also minimal class, right? And you can see that there is a pair of two edges. Well, there are multiple such pairs. For example, E and F, if you like. You delete E and F, and your graph is now disconnected. Both components are of even order. Therefore, E comma F is an even two cut. Right? And that's what the result is saying. That any minimal class will contain an even two cut of the given matching code graph. Of cardinality 3, sorry. Not any minimal class. Any minimal class of cardinality 3 or more. Yeah? Is the content of the result clear? So this is our next main goal. Yeah? Yeah, so one thing I want to mention is that the first time I saw this result was actually when I was teaching the same course as a contact course in 2022 December, 2023 January. Only people crediting the course were Aditya Narayana, and that was the first time I actually learned of this result because I was using a pre-print of Lucchesi Murty. It was not published yet, published in 2024. So I was using an unpublished version, And when I taught this, I was like, oh, very cool. And I was like, seems like some connection to ear decomposition theory. Either you need single ear or double ear. So this would say that every removable class is either a single edge or two edges, right? So yeah, good, nice. But now I'm like, wow. And that's because one of the reasons that made me appreciate this result a lot more is because of Narayana's thesis, right? He really exploited this result very nicely to get very cool consequences, something that I did not anticipate. But he was like, yeah, I'm going to use this dependence theory and throw it at my problem on solitary edges, and we had some really cool things. Anyways, so yeah, I have a much deeper appreciation, but that also means that I want to deliver a much deeper appreciation. So yeah, so I'm going to try my best to in the process of presenting this proof, I also want to simplify it as much as possible. I mean, I've already kind of been doing this in my head for the last couple of days, and I think I have something that is simpler in a sense. But that doesn't mean that what I will present will be shorter than what is there in Lucchesi Murty. I may actually make it a bit longer just to emphasize on certain points. Anyways. I will tell you what are the places where the proof can be improved as it is presented in Lucchesi Murty. Okay, so this is what we want to prove, and of course, because it is a minimal class of cardinality 3 or more, we will have edges that are mutually dependent. Any two edges in that class are mutually dependent, so we will find this useful. But before we prove this, let's do some more groundwork. Yeah. Okay, so let's try to see what we already know about minimal classes. What do we know about minimal classes in bipartite matching covered graphs? Bipartite matching covered graph. Yeah, what do we know about minimal classes? Singletons. Right? If there is a minimal class, it's a singleton. You can't have a doubleton minimal class in a bipartite matching covered graph. This is basically, I think if I'm not mistaken, this was 8.1, the very first result in this chapter. In a bipartite matching covered graph, every minimal class, of course it may not exist, that is a different matter, but if it exists, then it is a singleton. Yeah, that we already know.
What about
Hmm?
What about even cycles?
Even cycles, no minimal class. Oh, good point. Removable class. Thank you. Yeah, sorry. Every removable class is a singleton. Good, thank you. What does that mean? That means that a minimal class, except for K2, is either removable, right? If it is a singleton, and if it is not a singleton, then a minimal class will actually not be removable. Do you all agree? A conclusion of this, yeah, this is the point I wanted to make, is that in a bipartite matching covered graph, so let's say G is a bipartite matching covered graph, and let me say it is not K2. Okay, let's throw away K2. Going to shut down.
It's going
Yeah?
10%.
Okay, how much?
10%.
10% remaining. Okay. Alright. This is unnecessarily stressful. Okay. Yeah. So if you have a bipartite matching covered graph that is not K2, then a minimal class, if it's cardinality 1, it's actually removable. Do you all agree? If I have a minimal class of cardinality 1, I cannot disconnect the graph by deleting one edge because it's not K2. Every other matching code graph is 2 connected. So if Q, so let me say Q is a minimal class. Yeah, let's say Q is a minimal class. If the cardinality of Q is 1, then Q is a removable class. Otherwise, you delete the edges of Q and now your graph must disconnect. Right? Otherwise, G minus Q is disconnected and Q is therefore not a removable class. You all agree? Right? Because the removable class we know is a singleton. Therefore, if it were not a singleton, then it shouldn't be removable. Therefore, the graph should be disconnected after I delete the edges of Q. Yeah? Okay? In fact, let's go a step further. Let's go deeper into this. So you have a minimal class whose cardinality is not 1, therefore it is at least 2. In particular, you have 2 edges that depend on each other. Let's try to understand mutual dependence in bipartite graphs. Okay? Let's look at this. What does mutual dependence look like? So let's say G is a bipartite matching code graph. E and F are 2 mutually dependent edges. Now I'm not assuming anything about minimality. Right? I'm just assuming that they depend on each other. So let's say G is a bipartite matching code graph. E and F are distinct edges and E and F are mutually dependent in G. Well, we already know what dependence looks like in bipartite graphs, right? This we have already discussed. Dependence looks like this, right? If something, once I delete the edge F, if I delete the edge F, the edge E is no longer matchable. That means that in my graph G minus F, the edge E looks like this. It is the only edge that goes from here to here. All other edges of the graph, they go from, so if this is my S, let me just call this A0, A1, B0, B1. So the only edge going from here, A0 to B1, the only edge from A0 to B1 in G minus F is the edge E, right? And now this edge is clear that this is not going to be matchable. Is that right? Once I delete F, sorry, give me a second. I've deleted F. Okay. Basically, there may be, no, I did not mean this. This is not true. This is the next step. I'm coming to this one. Once I delete the edge F, I have some graph, some edges that are not going to be matchable. In particular, E will not be matchable. That means I will have a situation like this. To make the drawing nicer, I will have a situation like this, where all edges go like this, or like this. There are no edges from here to here in G minus F. That's what I mean. In G minus F, no edges from B0 to A1. But since I've deleted only one edge and my graph is not K2, right, because I have two distinct edges, my graph is still going to be connected. So therefore there will be at least some edges from here to here. It can't be that there are no edges in this cut. There have to be some edges and they all go from A0 to B1. There are no edges from B0 to A1 after I delete F. So where is F? F has to go like this. Otherwise these edges would be unmatchable even in the graph G. So F has to go like this. But now I want to ask you all a question. So F goes like this, right? F is the only edge in the original graph G that goes like this. Now I want to ask you, how many such edges? Can I assume that E is one such edge? Because E is going to be unmatchable after I delete F. So I can choose a cut that contains E, and E is one of the edges. But now I know that E and F are mutually dependent. So can I have more edges like this? Okay, I'll repeat a few things, right? So let me just do this argument again. I'm looking at the graph G minus F. E is unmatchable. You all agree? In G minus F, E is unmatchable. But the graph G minus F is matchable. G minus F itself is matchable. So what does an unmatchable edge in a bipartite matchable graph look like? I claim that it looks like this. I have a set of vertices. I have this partition of the two sets. Maybe I'll do the same numbers, 4 and 4. And the edge E is unmatchable because E is one of the edges that goes from here to here, and there are no edges from here to here. This is the reason E is unmatchable. There are no edges from here to here in G minus F, and E is an edge that goes like this. Therefore, E is not matchable. Yeah? And there could be more such edges. There could be another edge like this. Right? I'm not saying E is the only edge. But now F has to be like this. And now I want you to observe that actually because they are mutually dependent, you couldn't have had another edge like this. Take a perfect matching containing E prime. Observe that it contains F but it does not contain E. If there was another edge, then you would have a perfect matching containing E prime. It will have to contain F and it will not contain E by counting. You all agree? So therefore, in a bipartite graph, mutual dependence looks exactly like this. It's an even two cut. Yeah? Okay? So, the conclusion is in any bipartite matching curved graph, distinct edges Alright, back to where we were. So the conclusion is that in a bipartite matching curved graph, distinct edges E and F are mutually dependent. If and only if E comma F is an even two cut. So you may say, well, we did not really prove the other direction. Actually, the other direction is not difficult. If you have an even two cut in a bipartite graph, so you're deleting two edges and you are getting two components. You can't get more than two components, otherwise you'll have a cut edge in the original graph. So I've deleted two edges. Let me make sure I'm not missing any cases. C2. Yeah, sure, of course, yeah. Okay, fine. Alright. I'm deleting two edges. You can also assume that they are non-adjacent edges, right? So I'm deleting two edges and it is an even two cut. So it definitely cannot be, right? So I get two components. Right now I don't know whether the cardinalities are equal or not. I'm drawing it like this. Supposing I delete two edges and I get an even two cut. Right? So I have an even two cut formed by these two edges. This is my one component G1 and this is my other component G2. All I know is that they are of even order. Even number of vertices, even number of vertices. But the original graph is bipartite matching covered. I'm assuming I'm looking at the other direction. Supposing I have two edges that comprise an even two cut. So I delete the two edges. I'm looking at G minus E minus F. And I got two components of even order. Yeah? But the original graph is bipartite matching covered. So therefore, it must be that these two are equal cardinality. If one of them is smaller than the other, then even after adding the edges, you will not be able to compensate for the neighborhood. The neighborhood for every set should be at least one larger than its own size. That you can't achieve. Right? So, therefore, if two edges comprise an even two cut, then these two actually are equicardinal. One edge goes like this. Now the neighborhood is big enough. And by symmetry, the other edge goes like this. Now the neighborhood is big enough for all sets. It's just a little bit of arithmetic. You just have to write down the cardinalities and just do some straightforward math to see that this is the only possibility. Okay? And now you can observe that every perfect matching that contains this edge also contains this edge and vice versa, mutually dependent. Right? So, this is a complete characterization of mutual dependence in bipartite matching covered graphs. It's exactly the even two cut case. Right? And this proves the result we want for bipartite matching covered graphs. If you have any minimal class, you don't even need cardinality 3 or more. Cardinality 2 works. If you have a minimal class of cardinality 2 or more in a bipartite matching covered graph, take two edges in that class. They are mutually dependent, they form an even two cut. Result is proved for bipartite graphs. Okay? So, proved for bipartite matching covered graphs. Yeah, convinced? Or did I cheat you? No? Okay. Alright, so next what we will do is we will prove it for bricks actually. Actually, we almost proved it for bricks last time. We just have to go one step further. We'll do it again. Yeah? So you may recall that I was somewhat tempted to look, after discussing this result, I was like, hey, what happens if it is a brick? And then we discuss a bit more, right? So supposing I have a brick, G is a brick, yeah? And let's say I have two mutually dependent edges in a brick, yeah? E and F are distinct edges, and let's say that E and F are mutually dependent in G, yeah? Now we can apply 8.13 for any matching covered graph. If I have two distinct edges that are mutually dependent, I have this very nice drawing, and one of the things we wrote here is this: for every odd component, the partial of that component, the cut corresponding to that component, is a tight cut. What does that mean? What can you say about each odd component? The graph is a brick. Huh? Trivial. You all agree? The barrier has at least two vertices because the edge E has both ends of the barrier. So the other shore is definitely non-trivial. So therefore this shore, the component itself, has to be trivial. Yeah. So if we apply 8.13, which we proved last time, we have this figure. We have a barrier, we have the edge E, both ends inside, and all these components are trivial, and the edge F is like this. This is very close to being bipartite. You remove the two edges E and F, and now what you have is a bipartite graph. It may not be matching covered. It may not be matching covered, that's okay. But it is bipartite. Yeah? So what we have proved is that G minus E minus F is bipartite. Yeah? So if you have two mutually dependent edges in a brick, then you delete the two edges, you have a bipartite graph. Is it matchable? Can we at least say it is matchable? Yeah? It is matchable, right? The original graph was matching covered. This graph is still matchable. It may not be matching covered. We won't use that fact actually. Well, we will in some weird sense, I don't know. Also matchable. But actually we won't really use the matchable fact. We'll just use the fact that it's bipartite. Yeah, you all agree? So we know that for any two mutually dependent edges in a brick, distinct edges, you delete the two edges, you have a bipartite graph. A bipartite matchable graph to be precise. That doesn't prove what we want. What we want to prove is if there is a minimal class of cardinality 3 or more, then it contains an even 2 cut. It's strange, right? Even 2 cut in a brick. This is strange. So what should we actually prove? I mean, we will prove this statement because it is for all matching curve graphs. But somehow we should not be able to conclude that a brick has an even 2 cut. So therefore, what should happen in a brick? What should go wrong? Every minimal class should have cardinality at most 2. You shouldn't have a minimal class of cardinality 3 or more, because then you would prove this theorem and then you would say that a brick is not 3 connected. That's the problem, right? So what we will prove is that you can't not only have a minimal class of cardinality 3 or more, you cannot have any equivalence class of cardinality 3 or more. This is what we will prove. We will prove that in a brick, every equivalence class has cardinality 1 or 2, minimal or not. Yeah, this is what we will prove. So the goal is to show, and I claim that we are actually very close. The goal, and some of the things we are covering are from chapter 9. But yeah, I feel like going in this way. So we have already started chapter 9 simultaneously. So what we will prove is that in a brick, so G is a brick is already written, every equivalence class has cardinality at most 2. Okay, this is what we are going to prove. What we have so far is we have that if you have two mutually dependent edges, then G minus E minus F is bipartite. Okay, from here we want to go here. Okay, this is what we want to do. Let me just mark it. So what we have is the stuff in yellow. E and F are mutually dependent edges. Then G minus E minus F is bipartite. From here we want to go here. Yeah? From 2. Yeah? I want you all to think. How will you do that? How will you go from to 2? And I will give you a hint. SGT. Don't forget SGT. Module 1 actually. I'll erase this. Suppose you have an equivalence class of cardinality 3 or more. Yeah? So G is still a brick. Suppose there exists an equivalence class of cardinality, let's say Q, such that Q has at least 3 edges. I don't know what to do. I know, but if I have two mutually dependent edges, then I can do something. So let me say D, E and F are distinct members of Q. Supposing I take 3 distinct members of Q. Now for each pair, I can apply what I know. G minus E minus F is bipartite. From here, I know that G minus E minus F is bipartite. And I know that G minus D minus E is also bipartite. And I can also write down the third pair, why not? I may not use all 3. All these graphs are bipartite. How is that happening? You delete D and E bipartite, E and F bipartite, D and F bipartite. I have this drawing for E and F. I can make another drawing for D and D. Let me keep E on the top. You can make a third drawing if you like for D and F. I won't make that. In particular, there is a DIY in STT that is related to this. I memorize all the DIYs. I mean, intuitively it seems like this should not happen, right? Intuitively I agree. But so maybe what you're thinking can be converted into a formal argument. But there is something even fundamentally simpler. So try to recall what all module 1 covers in STT. What are the concepts that we cover in module 1? So module 1 is about two vector spaces, right? The bond space and the cycle space. Why are they vector spaces? What is the operation that we consider when we say that something is a vector space in that module? XOR, symmetric difference, right? So the symmetric difference of two elements in one of these spaces is again an element in this space, right? One space, its elements are even subgraphs. Subgraphs in which every vertex has even degree. That doesn't seem very useful here, right? I mean, cycles, sure, but even subgraphs I don't think are very useful here, right? The other one, in some sense, is much more natural in any context in matching theory, in any context in graph theory for that matter. Cuts, right? The bond space is simply the cuts of a graph. And therefore the symmetric difference of two cuts is a cut. Right? We proved that, right? Partial of x symmetric difference partial of y is simply partial of x symmetric difference y. In particular it is a cut. So now can you see? Now, this is the hint. So the first hint is the symmetric difference of cuts is a cut. There are some cuts staring at you. In these drawings, there are some cuts that are staring at you. What are those cuts? So this drawing, there is a cut that is staring at you. And this drawing also, there is a cut that is staring at you. In fact, I claim that in any bipartite graph, there is a cut staring at you. This was an exercise in the DIY. E of G is a cut of G if and only if G is bipartite. No, DIY. Too easy for assignments. This hint 2. In some sense, you don't really need this whole hint, but this hint still hints something, if I may. Right, that is correct. To characterize non-cuts, the problem with the part with 7 marks, that requires, well, if you use this, it is kind of nice. Right. Yep, okay, so think about it and I'll come and talk to you. Anyone? you have identified the cuts. Now pay attention to what are the edges you will get in that cut. Okay, good. So the point is, once you have this drawing, we'll use blue or something, I don't know. Here, you have a cut of the graph. This is all edges of G minus E minus F. Here you have a cut of the graph. This is all edges of E minus B minus E. Both of these are cuts of the graph. Therefore, their symmetric difference is also a cut of the graph. And their symmetric difference is just D comma F. Right? So, we are using EF and DE, these two. So, from this we conclude that D and F is a cut of G, but G is a brick, that is 3 connected, it cannot have a 2 cut. Contradiction. Since G is 3 connected. Yeah? Isn't that really cool? Yeah.
So this is enough for Narayana's theorem.
No. Depends. So if you think of Narayana's result as a result for bricks, then you don't need more.
You're only using the fact that it's 3 connected.
No. We used the fact that it is a critical graph earlier. No. So actually, that's a very good point. That's a very amazing point. You may say, we use the fact that the graph is 3 connected here. So maybe this statement is true for all 3 connected graphs. But we also use the fact that it is a brick and not just 3 connected somewhere else in the beginning. It is not true. In fact, one of the results, one of the papers that made me much more comfortable with dependence is a paper where we prove, this is with Fuliang and others, that for any 2 integers k and l, I can give you a matching code graph that is k connected and has an equivalence class of cardinality L. Yeah, it won't be minimal. It won't be minimal. Because if it were minimal, then you would have an even 2 cut, then the graph would not be k connected for an arbitrary large k. Yeah. Right? So in fact, that's a very good point. So did you catch how we concluded? Okay. So I'll just quickly repeat that point. So this is a cut of the graph. Observe this picture. This is a cut. This is a cut. What is the symmetric difference? This is a cut of the graph, but the graph is a brick, it is 3 connected. You can't have a 2 cut, right? The point is, we have not just used the fact that the graph is 3 connected. In the very beginning, we used the fact that the graph is a brick, when we concluded that all these are trivial. That was very crucial. So the statement requires brick. It requires both 3 connected and bicritical. Right? And in general, you can choose any 2 integers k and l, and there is a matching code graph whose connectivity, vertex connectivity as we call it, is at least k, and there is an equivalence class of cardinality L or more. But of course it will not be minimal, because otherwise your graph could not be very well connected. So those equivalence classes will in fact therefore not be minimal. Yeah. But for bricks we proved very strong things. So in the case of bipartite graphs and in the case of bricks, we are done with this result for different reasons, right? Let's just summarize that really quick. So we are done for bipartite graphs and we are also done for bricks. And in both cases we proved stronger statements. Here what did we prove? We proved that any two mutually dependent edges, they comprise an even two cut. Therefore, any equivalence class of cardinality 2 or more will contain an even two cut. Yeah, that was the case for bipartite graphs. For bricks, we proved that every equivalence class has cardinality 1 or 2. So therefore this never happens. Therefore you never need to prove anything. Yeah? Yeah? So we're done with these two. Alright. And as I said, some of these results, the brick part is from chapter 9 actually. But I want to do it this way. Yeah. Because I feel that it kind of draws more upon previous thing covered in the course. Okay, so we are done with bipartite graphs, we are done for bricks. Now suppose you have a matching covered graph that is neither bipartite nor a brick. Well, in particular it has a non-trivial tight cut. So we should try to prove this statement by induction. Let's see what happens when we try to do that. Yeah. Okay. I'll get rid of this stuff. So let's say we are attempting to prove theorem 8.17 using tight cuts as our induction tool. So the proof is, or at least the attempt, is using induction on order. If the graph is bipartite or a brick, we are done. Now suppose that G is neither bipartite nor a brick. In particular, G has a non-trivial tight cut. Let's say C partial of I don't know, I'll use S. Okay, is it right? So we have a non-trivial tight cut. Okay, let's see how we try to prove this statement using tight cut as an induction tool. So this is my vertex set. This is my set S. This is S bar. And I consider two contractions. What else will I do in life anyways? This is little s bar, my graph G1, this is my set S. This is S bar, this is little s, and this is my graph G2. Yeah? And the edges of the minimal class, so Q is our minimal class. Q is a minimal class. Of cardinality at least 3. Right? And what we are trying to prove is that Q contains an even 2 cut. There is a set of 2 edges inside Q that will comprise an even 2 cut of the graph G. So how shall we now proceed? Right? I mean, we are not going to finish the proof immediately. Right? We may not even finish it today for that matter, which is okay. But how would you now proceed? So I am trying to use this result as a natural result where you would try to use induction using tight cuts. Basically, you would try to understand this minimal class across tight cuts. Or more generally, how do minimal classes or equivalence classes behave across tight cuts? That's sort of the rationale behind trying to do the proof this way. And at some fundamental level, this is what they actually do, right? But it's more complicated than this. We'll get to that more complicated thing later. But this is the most basic thing one would try to do. Consider a non-trivial tight cut and see if you can finish the proof by induction. Right? But of course, to apply induction, you need to know something about the minimal classes of these two graphs. In particular, how does Q help in these two smaller graphs? Does it help? So I want you all to think about what you would try. The edges of Q could be anywhere in this graph. Actually, that is something worth thinking about. What is the intersection between Q and this cut? How much can it be? Q is a minimal class. The cut is a tight cut. So Okay, yeah, so right, so everybody sees it follows from the definition of tight cut and minimal class or dependence class more generally that the intersection of Q and C is either 0 or 1. Yeah, great. So observe that the intersection of Q and C is either 0 or 1. Yeah? So let's consider the case of 0 for a moment. Supposing it is 0. First suppose, I want to almost say 0 suppose, but anyways. First suppose that Q intersection C is empty. That means all the edges of Q are here and here. Can they be in both places? Could it be that an edge of Q, one edge of Q is here, E1. There is no edge here because we are in this assumption. And another edge of Q is here. Can this actually happen? That's one point. Could it be that a minimal class has an edge in both shores, one here and one there, but nothing in the cut? If we can somehow conclude that this is not possible, then we would actually be able to make a lot of progress on this case. If we can conclude, right? Or we don't conclude this and we do something about this case also. Right? So is it possible that some edges of Q are here and some are here, but nobody is in the cut? And another thing, as you can already see where this is all going, we should consider the restriction of Q to G1 and G2, and we should pay attention to this restriction. So we can call them Q1 and Q2, right? So let's say Q is my set of pink edges. So in general, we will use Q1 and Q2 for the restrictions. Qi is Q intersection edge set of Gi. Right? What can we say about the Qi's? Yeah, and this is also independent of this case. So in this case, what can you say? But even in the other case, when the intersection is 1, can you make a general statement about Qi's? What would that general statement be? And there is of course another question that is more general here, which is if two edges are dependent in G, then what can you say about the same two edges in G1 and G2 if they exist in those two graphs, right? So the more general question is, if I give you the tight cut in a matching code graph, can you say something about the dependence in the smaller graphs based on dependence in the original graph? What exactly is it? And I'll probably erase things here. Okay, so okay. That's okay. We are not going in that direction. We want to go in the other direction, right? Because we are trying to go from G to G1 and G2. Right? Later you can also think about the other way. But yeah, the point is that so this question is actually good to answer. If you answer this question, then you can kind of answer most questions here. That's the sort of. So think about two edges in G1. E and F. If E depends on F in G1, observe that then E also depends on F in G. Because if E were not to depend on F in G, then you take a perfect matching containing one and not the other, take a restriction to the smaller graph because it is a tight cut, right? For a tight cut, what do we know? The definition is every perfect matching meets the cut in exactly one edge. So I can take the restriction of the perfect matching here, and I have now a perfect matching of this graph. This doesn't happen for separating cuts. In a separating cut, you could be using three edges from the cut. Now the restriction is not a perfect matching. It is what we would call a lambda matching or something, right? Where one vertex is degree 3 or more, and the other vertex is degree 1, right? Whereas for tight cuts, it's very nice. Restriction is again a perfect matching. So just based on this, you can conclude that the dependence relation in Gi is simply the dependence relation of G restricted to edges of Gi. Right? You can restrict the relation to a subset of the edges. Right? And that is what it is. So the conclusion here is the dependence relation in Gi is precisely restriction of dependence relation in G to the edges of Gi. Convince yourself of this. Right? You simply restrict the relation to those edges, and now you have a dependence relation in Gi. What does that imply about the Qi's? This immediately tells you that Qi is either a minimal class of Gi or it is empty. It could be empty, right? This immediately implies that Qi is either a minimal class of Gi or simply the empty set. Nothing is stopping it from being the empty set. If it's an empty set, well, then it's not an equivalence class. Right? Equivalence classes are by definition non-empty sets. Right? Yeah. So that's the possibility. Good. So what we have is, we have an empty set or minimal class here, and similarly we have empty set or minimal class here. You agree? And we also know that the intersection of the cut is either 0 or 1. That also we know. Okay. Now let's go back to our case. All these discussions we did had nothing to do with this case. Okay? Whether intersection is with a cut is empty or not, these observations are not dependent on that. So maybe I should erase that from here. Okay, so this is all generally true. This is also generally true. We are going somehow like this. And now we are in the case. case 0. Q intersection C is empty. Yeah? Yeah, I don't think I'm in the mood for a break, so I'll keep going. Will the recording keep going? Or will the recording stop and I'm forced to take a break? Okay, maybe we'll take a break after this. Let's see. Q intersection C is empty. This is one case. So now I want to go back to that question. Can we have edges on both sides? One here, E1 here, E2 here, at least one, and nothing in the cut. Can that actually happen? Right? You know that the restriction, now we have more information. Now we know that Q1 is a minimal class of G1, Q2 is a minimal class of G2, and neither of them uses any edge from the cut. Right? Can that happen? Remember, when you delete a minimal class, you may not have a matching covered graph, but every edge is matchable. Every edge is matchable. Right? So if Q1 is using some edges from G1 and Q2 is using some edges from, both of them are non-empty, that's what I mean. If both Q1 and Q2 are non-empty, yeah, maybe I should write down. If Q1 and Q2 are both non-empty, that just means that there is at least one edge here, there is at least one edge here, and nothing in the cut. That's the case we are in. So now what you can do is, you can take a perfect matching of G1 containing Q1. It's an equivalence class. So the whole class will be in the perfect matching or nothing will be in the perfect matching. Right? So I can take a perfect matching of G1 containing Q1. It will use some edge from the cut, right? Now I will go to this graph, supposing it uses some edge F in the cut. Now I will take the same edge F here, and I will take a perfect matching of G2 minus Q2 containing this edge, right? When I delete a minimal class, my graph has the property that every edge belongs to a perfect matching. So I can take a perfect matching of G2 minus Q2 containing F. Now the union of these two perfect matchings is a perfect matching of the original graph that contains Q1 but does not contain Q2. Contradiction. Q1 union Q2 was a minimal class. Yeah? So therefore, if both of these are non-empty, then this is not possible. We just got a contradiction. So, sorry, both of them are non-empty. Sorry. If both of them are non-empty, we have a contradiction. Right? We took a perfect matching here containing Q1. It will contain some edge F. We took a perfect matching here in G2 minus Q2 containing this edge. Every edge belongs to a perfect matching. Minimal class. You can disconnect the graph, but you cannot change the fact that every edge belongs to a perfect matching. That property still remains because of minimality. Right? So yes, so we may have a graph that is not matching covered. That's okay. Every edge belongs to a perfect matching. Sorry?
Components are matching.
Exactly, components are matching code, right? So you take a perfect matching of G2 minus Q2 containing the edge F. Now your union is a perfect matching of G. Q1 is in that perfect matching and Q2 has empty intersection with that perfect matching. Contradiction, because Q is a minimal class, it's a class. Good. So this is not possible. Both can't be non-empty, right? Therefore, what does that mean? That means that all the edges, one of them is going to be empty. One of them is going to be empty. There are no edges of Q here in G2. That means all the edges of Q are actually here. That's great actually. Then you have a minimal class in G1 whose cardinality is 3 or more. If there are no edges here, that means all the edges of Q are here. Then you have a minimal class in G1 whose cardinality is 3 or more, because we already proved that Q1 is either minimal class of G1 or it is empty. It's not empty, all the edges are here. So this is going to be a minimal class of G1 of cardinality 3 or more. By the induction hypothesis, it contains an even 2 cut. Every 2 cut of G1 is a cut of G. Right? That's nice. So you're done. This proof will be finished. Right? Good. Yeah? In fact, now we can go back to forget case 0. Now let's do this whole thing more generally. Now I am allowing both possibilities. Either there is an edge in the cut or there is no edge in the cut from Q. Right? If there is in fact, if there is no edge in the cut, we are already done, right? Proof is finished. Is that right? If there is no edge in the cut, we concluded that all the edges are in one graph, and now you just induct and you finish the proof. Okay, so let me just consider there is one edge in the cut. So now we are in this case. Yeah? So one edge is in the cut, one edge from Q. Q is my pink colored edges. One edge from Q is here. Therefore, all the other edges of Q are going to be not in the cut. Some could be from the left side, some could be from the right side. If there are at least 2 on the left side or at least 2 on the right side, then we are done again, because now we have 3 edges in at least one of the 2 contractions. By induction hypothesis contains an even 2 cut, proof is finished. So the only case that is not done is the case that you showed to me. This case. One edge in the cut, one on the left side, one on the right side. In this case, neither of them has a minimal class of cardinality 3 or more. Right? We want Q1 or Q2 to be cardinality 3 or more. But in this case, I have cardinality 2 here and cardinality 2 here. I cannot finish the proof by induction. At least not immediately. In all other cases, we are done. Yeah? So I want you all to appreciate this case. The only case where induction doesn't finish the proof is this case. One here, and one in the cut. In all other cases, we are done by induction. Yeah? Okay. Let's take a break. Yeah? Are there any questions or concerns before we stop recording? Is this part clear? Everybody agrees that this is the only bad case? Yeah? Remember, this is a proof attempt. We will see the relevance of this in the actual proof. And the actual proof will actually use some of these things. Okay? So, this was just to give you an idea of what is really important in the proof. Right? Yeah? Okay. Thank you.